Kia ora and welcome to this video on question 4 of the 2016 Scholl Calc exam. All three parts are set in the conics context, so it is quite possible that you haven't done much conics at school, given it's an internal assessment. It's also one of the hardest questions I've seen in scholarship over the years. Even with a good understanding of conics, the algebra is really intense. Part A isn't too bad. Part B has a trick that you can solve the problem in a couple of lines if you know it. So students from a Cambridge background are definitely advantaged there. And then part C is absolutely insane. And I'll be honest, right now, this is actually my second take of the video because the first one didn't go so well. Alrighty, first question. Let's just do a little bit of basic understanding of conics first. We've got this hyperbola in here, and we're told it has the equation x squared over, x squared over 4? Yeah, x squared over 4 minus y squared over 36 equals 1. So if we think first up, what are the x-intercepts of that hyperbola? So when y is equal to 0, we get x is plus or minus 2. So this x-intercept here is 2. And that's the first thing to know in a hyperbola. If you've got x squared over a squared minus y squared over b squared equals 1, then x equals a will be this distance here. Okay, the other thing you should know in when dealing with hyperbolas is that b doesn't appear on the hyperbola, but it determines the slope of the asymptotes of the hyperbola. So those lines L1 and L2, there are asymptotes. The hyperbola is tending towards them as x gets really large. So if I rearrange this equation, the hyperbola equation, so I've got y squared over b squared is equal to x squared over a squared minus 1 times everything through by b squared, and then square root that, plus or minus. We say what happens as x gets really large? As x tends to infinity, well, the minus b squared term is going to be negligible. As x gets really large, taking away a value b squared is not going to do much. So as x tends to infinity, y is going to tend to plus or minus root b squared x squared over a squared, which is plus or minus b over ax. So in other words, if we zoom out, the hyperbola is tending towards a straight line as x gets large. Okay, so knowing that the asymptotes have a slope of b over a and minus b over a enables us to put in a rectangle in here using the slope of the asymptotes. Also using the equation of the asymptote. And because I've already said that a is equal to 2, and we know that the slope is b over a, this rise here must be b. And from the question itself, b is 6. A squared was 4. B squared 36, so b is 6. Okay, so that's enough to actually be able to solve the first problem. So we go up to the question and let's actually read it. P is a point on the right branch of the hyperbola. Okay, so P's drawn there for us. Theta is the angle between the two asymptotes, L1 and L2. Show that sine of theta is 0.6. Okay, so we've got our theta drawn in there. What you can't do, because this is a dodgy method, what you can't do is find this angle here, alpha, using trig. If you do that, you've got tan alpha equals 6 over 2, so 3. Find alpha by just taking the tan inverse. Notice I said you can't do this. Let's work in degrees. It comes to be 71.5 0.565 degrees, because as soon as I've reached for a calculator, I'm in a non-exact method. So we've got that, and that means that theta is equal to 180 minus 2 lots of that. It will enable us to get the answer though. 180 minus 2 lots of that. It's actually 870 to 3 dp. And then sine of theta is the sine of that, and it comes out to be 0.6. Now I haven't actually proven that, I've just used the calculator to get it. So part A, how would we actually solve this properly? Well, we can start at tan of alpha equals 2/6 if we want, but actually more useful to us is probably this triangle in here, because we can bring in theta straight away. Okay, and if I look at the angle, there's theta over 2. So I've got tan of theta over 2. Do I want tan? No, the question's asking us for sine of theta. So actually there's a double angle formula. Sine 2 theta is 2 sine theta cos theta. So sine of theta, if I half the angles on the right hand side. Those are the trig ratios I need. Sine of theta over 2 and cos theta over 2 are what I need to be able to work out sine of theta. So if I use Pythagoras with the sides 2 and 6, so I've got the sides 2 squared plus 6 squared is 40, so the hypotenuse is root 40. And then I can use that yellow triangle, 6 there, 2 there. So sine of theta over 2 is opposite over hypotenuse, so 2 over root 40. And cos of theta over 2 is adjacent over hypotenuse, so 6 over root 40. And that comes out to be 24 over 40, which is 0.6. Okay, and I've worked in exact form the whole way down. There is another way of doing this problem, and it's to use areas. If you think about how the area of a triangle formula is constructed, the area of a triangle is half AB sine C, where A and B are sides and capital C is an angle, or it's a half base times height, where B and H are at right angles to one another. So if I look at the, now I'll just look at the whole triangle, because I want theta as my angle. So the whole triangle there, if I went and found the area of a triangle using the half AB sine C formula, it'd be going half times root 40 times root 40 times sine of theta. But if I was using the half base times height formula, the base is 4. Okay, it's 4 across and 6 high, so it'd be going half times 4 times 6, and then I can use this equation equating the areas to get sine theta. Sine theta is equal to 24 divided by 40, and I get the same answer as before. So that's quite neat. Now this area of a triangle formula, we're going to use that in part C when it looks at minimizing the area of a triangle. I guess that first question is not too nasty, but you did need to know about the asymptotes of a hyperbola and that their slope was b over a. And you also needed to bring in sine of theta somehow, whether it was using trigonometry or the area of a triangle. Okay, let's look at the second question. From P, lines are drawn perpendicular to the asymptotes. So we've got a line going through there, which is the line PA. And we know what the slope of that line is. We know that the slope of the asymptote is 3, so we know that the slope of that line is minus 1/3 if they're to meet at right angles. The gradients are negative reciprocals. Let's call P x0, y0. They do this in the schedule. It's a very common thing to do in conics. X0, y0 is a specific point on the curve, and we can write these equations in terms of that. We use the equation of a straight line. Y minus y0 equals negative 1/3 the slope x minus x0. Okay, it goes through the point x0, y0. And then the other line, the line PB. Okay, well that one here has a slope of positive 1/3. L2 has a slope of negative 3, so the normal must be y minus y0 equals 1/3 x minus x0. Now why are finding those equations useful? Well, what we can do then is use those equations to find the point B and to find the point A, because the question says show that the product of the lengths of the two segments PA and PB is constant. To find the length of PA and the length of PB, we need to find the coordinates A and B. They're going to be both in terms of x0, y0, and then we can use distance between points to find those lengths. It is still a pretty hard question. So before we jump into it, let's just have a look at the answer to the question, because I've made a GeoGebra diagram to get my head around this. I've got the hyperbola in there, I've got the asymptotes drawn in there, and I've got these lines, these perpendicular lines, PB and PA, already in there, ready to go. Now the numbers that are on the diagram there are the lengths of PA, or the distance between P and A, and the distance between P and B. And when you multiply those numbers together, you apparently get a constant. On the left hand side of my diagram there is, under the number thing, there's a little A equals 3.6. That is the product of those two lengths. And if I move the point P to a different position, of course AP and BP change, but the product is still 3.6, which means that to find the answer to the question, I can move it to a trivial position like this point, where point P is at the point x equals 2, the vertex of the hyperbola. That forms a kite shape, where both the length AP and BP are the same, and it also makes a right angle triangle with the x-axis and the asymptote. And I can use basic trigonometry to find the value of AP. So if we consider a trivial position for P, like the vertex, and then A will be this point up here. That's a right angle. We know this length is 2. We also know this angle from earlier, this angle alpha, or we at least know it's related to this triangle here. The slope of the asymptotes was 3, so it was like 1, 3. Not necessarily the sides of 1 and 3, but the ratio is tan alpha equals 3. And from that, we can find the area of that triangle. So we've got half base times height. AP, length AP, which we're trying to find, because we also want to find the length down here, which is the same. Now that length there is 2 sine alpha, and from our diagram there, 1, 3, this one will be root 10, so sine alpha is 3 over root 10, so AP is 2 times 3 over root 10, and that means that our product, AP times BP, those are the same length at that position, so we've got 6 over root 10 times 6 over root 10, which equals 36 over 10, 3.6. Okay, so that's what we were getting in the GeoGebra diagram. But of course we can't just consider a trivial position for P to prove that it's constant, but if it's constant, that will be the value. So let's go back to our method of attack here. Finding the length of PA. I said at the start of this video, if you've done some Cambridge maths, you've probably seen this formula here before. This is the way that they do it in the mark schedule. The distance between a point and a line. Okay, so we've got a line which is y equals 3x, and we've got a point x naught, y naught, and we want to find the distance between that point and the line, which when we say distance, we mean straight line distance or perpendicular distance. And the formula for that, I'm just going to Google it again because it's not something I memorize. Okay, it says the distance is equal to the absolute value of ax naught plus by naught plus c over root a squared plus b squared, and the website gives a proof of it, where the line is in the form ax plus by plus c equals 0. So any straight line can be written in that format. Our line can be, we write 3x minus y plus 0 equals 0. That's the line y equals 3x. Okay, so if we apply this formula, did I say a couple of lines? I guess the first line is the formula and the second line is the answer. We've got the distance is equal to a, which is 3. Okay, this is my a, my b is minus 1, and my c is 0. So we've got 3x naught minus y naught, the absolute value of that, over root 10, 3 squared plus 1 squared. Okay, and the other distance, the distance between P and the other line, turns out very similar. Call that D1, D2 is 3x naught plus y naught all over root 10. So therefore the product is equal to all over root 10 squared, which is 10. Now it may seem that we're stuck there because we've still got the point x naught y naught sitting in our expression. However, these two things are just numbers. Like x naught y naught is a coordinate. When we work out that coordinate, it's a number. The absolute value times the absolute value of something else is equal to the absolute value of the product, which is a difference of two squares, so it simplifies to that. And then we know that x naught y naught is on the hyperbola. So x naught y naught satisfies the equation x squared over 4 minus y squared over 9 equals to 1. So if I take this equation and times the whole thing through by, it wasn't 9, it was 36. But if I times the whole thing through by 36, I get 9x squared minus y squared equals 36, and xy is a point on the hyperbola, so it could be x naught y naught, and therefore 9x naught squared minus y naught squared is 36, so the product equals 36 over 10, 3.6. Okay, so that's the method if you've seen this formula here and you're able to memorize it. But a typical NCA student's never seen that formula, and then to memorize it, well, there's so many things you could memorize in these exams, so how about we look at it a different way that doesn't assume that knowledge. Okay, so right back at the start, I talked about this being our strategy of finding the lines PA and the line PB in terms of x naught y naught. So if I copy all that stuff down, that will be our starting point. Okay, and to find the point B and to find the point A, we're going to use simultaneous equations. So first up, finding A, we take the line y equals, what line was it? It is y equals 3x, the positive asymptote, and our normal, which if I expand it out has that equation, and if we equate them, the x value that satisfies this equation is actually the x value of a. If I rearrange this, I've got 3 plus a third, 10 thirds xa equals x naught over 3 plus y naught, times everything by 3 and then divide by 10. xa is x naught plus 3y naught all over 10. Remember, we don't just want the point xa, we want the distance between the point P and A. So we also need the y value of A, which is just 3 times the x value. And if you do a similar approach with the other one, so we find B this time, you could probably skip a minute of this video because it's very similar. We've got y equals minus 3x this time, and y equals 3x minus x naught over 3 plus y naught. The perpendicular line is a little bit different. Solve these simultaneously. Again, times everything by 3, or move the third across, so you've got minus 3 minus the third, times everything by 3, and divide by 10. So we've got minus 10 thirds xb. Actually, I'll times everything by minus 3. Divide everything by 10, and you probably would have guessed that because it's very similar to the other point of intersection. And then the y value of B is minus 3 lots of that. Which looks a little bit tidier if I get rid of the minus out the front of it. Okay, so we've now got the coordinate xa, ya up here, and we've got the coordinate xb, yb, and now we need to use these to find the lengths AP. So the length AP is the distance between the x value of P and the x value of A all squared. So we need to take x naught off the xa formula. We've got xa minus x naught all squared plus ya minus y naught all squared, square rooted, and then the length BP, same thing, just take xb this time minus x naught, square it, yb minus y naught, square it. Okay, what do these things simplify to? Well, if I take xa and I look at xa and which is there, and I take 1 x naught off it, that's going to become minus 9x naught plus 3y naught all over 10. And then if I look at the y value and I take y naught off it, I'm going to get 3x naught minus y naught over 10 all squared. does that equal? Now I can pull out the 10 squared out of the denominator, out of the square root. I can pull a 3 out of this one, and I'd have y naught minus 3x naught, which is exactly the same as the other one. It's 3x naught minus y naught, but it's in a squared, so it doesn't matter if it's the wrong way around. So if I pull a 3 out of the first one, it's going to give me 9 plus another one. I'm going to get 10, lots of 3x naught minus y naught all squared. So the 10 comes out of the square root as root 10, divides by the 10, I get 1 over root 10, and then I've got 3x naught minus y naught. And it's important to note that y naught, if I look back at the diagram, this has a height y naught, and it's at the position x naught, and 3x naught will be this dude here, because the line is y equals 3x, and if I sub x naught into it, I get 3 lots of that. So 3x naught is bigger than y naught. So come to my square root thing. This thing underneath the square root is a positive. Underneath the square is a positive, meaning I can knock the square root and the square off without worrying about absolute value symbols. Do a similar thing for BP. I'll spare you the details, but you get 1 over root 10 times 3x naught plus y naught. And then we've got the answer that we had before, because AP times BP is equal to 1 over 10 times 9x naught squared minus y naught squared, which we knew was 36. So 36 over 10, 3.6. Wow, if you didn't think that was intense, wait to part 3. Part 3 is even worse. But of course, if you had that little extra bit in your toolbox, the distance between a point and a line, it wasn't as bad. Okay, third question. Consider a case where P is located in the first quadrant. Again, that's what we've been doing the whole time. Through P, draw another line CD. Okay, that's drawn for us in the diagram. Where C is on the line L1, D is on the line L2, P is between C and D, such that CP to PD is a ratio of 1 to lambda. So what that doesn't mean is that this length here is lambda and then the other length is 1. But it's in that ratio, lambda to 1. Okay, so thinking through this problem, we've got to minimize the area of the triangle COD. So let's just identify where COD is. That's a terrible line. Okay, so that's COD there. Now, half AB sine C gives us the area of that. That angle alpha is actually 180 minus theta. So I've got a half, the length OC, the length OD, and then I've got sine of 180 minus theta. Okay, it turns out that sine of 180 minus theta is the same as sine of theta. If you look at the graph, sine of 180 minus x, same as sine of x. So we already know that sine of theta is 0.6. So we've got a half of 0.6, we've got 0.3 OC times OD. Okay, that there is the area that we need to find, and we need to minimize it, so finding the lambda value that does that. I've made another GeoGebra diagram. Okay, so what does this diagram show? We've got a triangle there, the triangle OCD, coloured in green, and at the moment it has an area of 23.13, as we can see on the bottom left of the screen. Points C and D are fixed, and we're saying where should we move P so that that triangle is minimized. So if I move P, the orange dot at the top of the screen, what that's doing is tracking the area as a function of lambda. So at the moment, lambda is bigger than 1. On the left hand column, A equals 2.31, that's actually the value of lambda. And as we move P closer and closer, the area gets smaller and smaller until it's minimized, and then it gets bigger and bigger again. So P at this position here is a minimum area, and it turns out that the area of that triangle is 12, and A is equal to 1 at that position. You can see the coordinate that says area has an x value of 1, that's lambda, and it has an area of 12. So it turns out that 1 to 1 is the optimal ratio for that. And you can also see that the line CD is tangent to the point P. And I think the top scholar in this year, I was having a look at their paper to see whether they got the question right, and straight away they said the area of the triangle is minimized if the line CD is tangent to the line P, and I don't believe it was fully justified. You'd have to prove it. But the cool thing is, if it is tangent, then we can move P to a trivial position like we did with part B. Let's move it to the x-intercept. Let's move C to be vertically on top, and then we have an easy triangle to find the area of, because we already know the slope of that asymptote is 3, out 2 up 6. Notice the diagram's not to scale. Out 2 up 6 means that the length CD in that position is 12, and half base times height is a half times 2 times 12, which gives you an area of 12. Okay, so the minimum area is 12, and it's when it's a 1-to-1 ratio, but we just need to prove it. Brace yourselves, algebra's coming. Okay, so we're trying to find OC and OD, the lengths, so that we can find this area. We're going to find OC and OD in terms of lambda, because then it will enable us to differentiate the expression with respect to lambda and make it equal 0 and so on. So it is an optimization question. It's just a very, very hard one. Okay, so to find OC and OD, well, we know O is the origin. We need to find the points C and D. And the tricky thing about this is we don't have an equation. So what they've done in the mark schedule, it's quite clever, is they've said, let this here be the equation of the line, where K is the slope of the line, and according to the diagram, K has to be bigger than 3. It has to be steeper than the asymptote, otherwise it's not going to cut the asymptote. But we write the coordinates of C and D in terms of K and in terms of x0, y0 before we bring the lambda in. Okay. So let the line CD have equation y minus y0 equals k x minus x0. And again, we go about finding these coordinates just like we did with A and B. We find C by equating it to the line y equals 3x. Oh gosh. Yep, I've subbed it in this time. Last time I made y the subject of both of them, but it doesn't really matter. If I sub that in, 3x into the y value. And remember that this is the x value of C we're finding. So xc is this dude. And the y value of C, just like before, is 3 lots of that. Okay, and then find D, which is the same line, but the asymptote is negative 3x. So I rearrange this one. Oh, that was nearly a fatal error. I made a mistake in the earlier one. It's supposed to be 3 minus k. I think there was a mistake in the mark schedule as well. I was trying to follow it through, and leave a whole heap of gaps in their working. They just put arrows and say, hey, this goes to this. But it seemed to be a little mistake with a minus. It just wasn't following. This one here, k plus 3 times xc is kx0 minus y0. It's not xc we're finding here. Oh gosh, you can tell it's getting tricky when it gets sloppy like this. It's xd that we're finding. And then the y value of d is negative 3. Lots of this. Okay, so we want the length of OD multiplied by the length of OC times by 3. So, 0.3. Area is 0.3 times, the point C is just, the line OC is just the distance from the origin of the point C. So I take the x value of C, square it, take the y value of C and square it, so I get 9. Hopefully you can see why I put the 3 on the outside of the brackets rather than expanding it, because I got exactly the same thing in that. Multiplied by the other one, OD. All squared the x value, plus 9 lots of the other one. Okay, and then because the things underneath the brackets are the same, we've got that thing's repeated, and we've got that thing as well. They're different, but underneath the square roots are the same. So we've got 0.3 times the square root of 10 y0 minus kx0 over 3 minus k all squared times 10 kx0 minus y0 over k plus 3 all squared. Okay, I need to go into another page. So this is the area. Okay, we need to note here that kx0 is bigger than y0. And the reason for that is k is bigger than 3. We talked about that earlier. And for the same logic as what I drew in the diagram there, so kx0 will be somewhere up here if k is bigger than 3. So the reason why that's important is because when we deal with these square roots, we've got 0.3, we've got a root 10 and a root 10, so that makes 10. We've got a 3 minus k all squared, square rooted, but k is bigger than 3, so actually we need it to be the other way around. It's going to be k minus 3, and k plus 3 all squared, square rooted is k plus 3. And then this dude squared is the same as kx0 minus y0 all squared. That's the way we want it round when we get rid of the squared and square root it. So we've got kx0 minus y0 all squared, square rooted, but then there's 2 of them. Okay, so that simplifies to 3 over k squared minus 9 kx0 minus y0 squared. And I've got that in the schedule, but they skip a whole heap of steps. Now, what I did on my first attempt at solving this video is then I then tried to bring in lambda. And the way I did it is where's my diagram? I found the distance dp, because I've already found the coordinate d in terms of x0, y0, and the coordinate p, x0, y0, and then I found the distance CP, and then set one to be lambda times the other. And I rearranged that equation, and it gave me quite a simple expression for lambda. Actually, it gave me lambda was equal to y0 plus 3x0. Should have any brackets there. It gave me this over 3x0 minus y0 times k minus 3 over k plus 3. And I thought, okay, cool. Now I can somehow use that equation along with my area equation to get the area solely in terms of lambda. But I got stuck and it just wasn't going anywhere. So I had a peep at the mark schedule, and they didn't do that at all. So in the comments, if you manage to find a way of doing that, that would be awesome. But I certainly couldn't. Okay, so where did they go to next? To bring in the lambda, they use this sort of similar triangle understanding here, that if I drop a line down there, it's not a very straight one, but you get the point, and then I drop another line down here, because of the ratio of lambda to 1, the line PD to CP has a ratio of lambda to 1, so do the x values. This dude here to this dude here will be in a ratio of lambda to 1. So if this is x0, and this one here is xd, and this one here is xc, I can find x0 by taking xd, adding lambda over lambda plus 1. Lambda over lambda plus 1 is the fraction along this line that we go, times the distance between xc and xd. Okay, so what that means is x0 is start with xd, add on lambda over lambda plus 1 times the difference between xc and xd. Similarly, y0 is the y value of d plus this ratio lambda over lambda plus 1 times the total distance between yc and yd. And this is how you connect the x0, y0s and the lambdas together, and the k's as well. Okay, so x0, using the first one, xd k x0 minus y0 over k plus 3 plus lambda over lambda plus 1 xc y0 minus kx0 over 3 minus k minus xd again okay, and this simplifies because we've got one lot of this thing here minus lambda over lambda plus 1 times the same thing, so 1 minus lambda over lambda plus 1 all times by kx0 minus y0 over k plus 3 plus lambda over lambda plus 1, and I'm going to just write this term I haven't done, I'm going to write it the other way around, kx0 minus y0 over k minus 3. Now these things factor, this is some serious factorization, but the first bracket, 1 minus lambda over lambda plus 1, actually simplifies to lambda plus 1 minus lambda all over lambda plus 1, which is 1 over lambda plus 1. And then we've got a common common factor here. This dude appears in both the terms, and so does the lambda plus 1, so we can factor that out. And then the remaining bracket 1 over k plus 3 plus lambda over k minus 3. So that's x naught. Okay, we do a similar thing for the y naught equation. So equation 2 up the top there. We use that one. Y naught equals yd. Yd is minus 3 kx naught minus y naught over k plus 3 plus lambda over lambda plus 1 times yc minus yd. Yc was 3 lots of that, but I'm going to write it the other way around. 3 lots of kx naught minus y naught over k minus 3 minus yd again, but that's a plus because yd was a negative. Alrighty, now again what you need to notice is that this thing here repeats. It's there and it's there. So we've got minus 3 times 1 minus lambda over lambda plus 1 all times by kx naught minus y naught over k plus 3, and then we've got the last term which we haven't dealt with, 3 lambda over lambda plus 1 times kx naught minus y naught over k minus 3. Again, that first bracket simplifies, it's lambda plus 1, take away lambda all over lambda plus 1, so 1 over lambda plus 1. Here's a common factor of lambda plus 1, there's also a 3, lambda plus 1 there, there's this kx naught minus y naught thing. Apologies for the length of this video. So we've got minus 3 for lambda plus 1, kx naught minus y naught, all times by 1 over k plus 3 minus lambda over k minus 3. Okay, and we also, lastly, to connect it all together, we know that 9x naught squared minus y naught squared equals 36 because x naught y naught is on the hyperbola. So if I take 9 times the first equation squared, this equation here, this is x naught, if I take 9 and times that squared, 9 times 1 over lambda plus 1 squared times kx naught minus y naught squared times 1 over k plus 3 plus lambda over k minus 3. If you find an easy way to solve this problem, please let me know. Squared minus y naught squared, so that's this dude squared. Okay, so 3 becomes 9 over lambda plus 1 all squared, kx naught minus y naught all squared, 1 over k plus 3 minus lambda over k minus 3 squared, and that equals 36. Now what am I trying to achieve here? If I go back to this area, I've got kx naught minus y naught all squared in that area expression, and I've got k squared minus 9, and I'm trying to bring lambda in. So first up, if I divide everything by 9, so divide by 9, make that a 4, and if I times everything through by lambda plus 1 squared, lambda plus 1 squared, lambda plus 1 squared, lambda plus 1 squared there, and then I have a common factor of kx naught minus y naught all squared, so I can divide everything through by that, It's going to be over here. Our equation simplifies quite a lot. We've got 1 over k plus 3 plus lambda over k minus 3 all squared. Take away 1 over k plus 3 minus lambda over k minus 3 all squared equals this. Expanding that left hand side, lots of things cancel because you get 1 over k plus 3 all squared for the first bracket, take away for the second, so they're gone. You get lambda over k minus 3 all squared, take away lambda over k minus 3 all squared. The middle terms don't cancel. We get 2 lambda over k plus 3 k minus 3 plus another 2 lambda, so 4 lambda over k plus 3 k minus 3 equals 4 lambda plus 1 squared kx0 minus y0 all squared. You can cancel off the 4's on both sides and bring that bottom right thing up to the top left again. So we've got kx0 minus y0 all squared over k squared minus 9 equals lambda plus 1 squared over lambda. Don't let this question be your a representative of your typical scholarship experience. It's pretty evil. This thing here, so just copy this area formula down. Where was it? So many pages ago. This here is our area expression, which we wanted to somehow bring lambda into. Okay, area equals this. Well, that's quite promising because we've got that whole term there is sitting right in the line above it. So our area is equal to 3 lots of lambda plus 1 squared over lambda. Oh my goodness, we've got the area in terms of lambda. Yippee yay. Check it. When lambda was 1, we got an area of 12, and that works out to be the case, so we've got the right formula. Well, that convinces us we have. Expand the brackets and divide everything by lambda. That's the area in terms of lambda. Differentiate it. Lambda diffs to 1, 2 diffs to 0, 1 over lambda diffs to minus 1 over lambda squared. Make it equal 0 for the minimum area. Minimum area occurs when lambda equals 1, because it can't be negative 1, and therefore the area equals 12. Smiley face to finish the problem. Probably a sad face given how long the problem took and how many times I got interrupted by a leaf blower throughout the recording of this.